going back to PowerPoint, slideshow. Okay. So let's go over. So this is the NeuroExplorer. I started working on it maybe like in 1996, and first release was in 1998. So it will be 25 years next. Oh, it's the end of slideshow. What's wrong? Huh. Why I'm not seeing slideshow? Oh, okay. So what is NeuroExplorer? It started as a program to analyze spike data, because in the late 90s we didn't have much bandwidth, so it was mostly like timestamps. And then I gradually added more and more support for continuous signals. So NeuroExplorer is the de facto standard in data analysis of electrophysiological data. I know that it's been used in hundreds of laboratories. I just listed a few of them so you can show the customers that kind of leading universities use this product. And if I do a search on Google Scholar, it gives me, the problem is that it used to be Micro Brightfield NeuroExplorer product, then there is somebody else called something NeuroExplorer, so you have to kind of filter them out, but still it gives me like 2,900 publications citing the program. Also, it's good to know that NeuroExplorer comes with a documentation that's first we have a web-based. So I told Eric before that you can easily translate it into Chinese. I don't know or I told to one of my Chinese customers. So if you go to this neuroexplorer.com/docs, you will see documentation, and you can, like for example, start looking at the tutorials, and you can translate this into Chinese if you need to. Also, the program comes with the manual that's currently more than 500 pages, and of course there is a help inside the program. With support, especially with China, with time difference, it's mostly email support. In rare cases, like when the customer has something doesn't work, for example, the dongle doesn't work, I had this with one of my customers in Hong Kong. So we had to do a Skype session and kind of figure out why it doesn't work. But usually it's email, and I usually answer it within 24 hours. Another kind of good to know for your customers is that the program is highly customizable, and a lot of requests can be solved by scripting. And in most cases, what I do is I talk to a customer, I write initial script, and then kind of customer can later modify the script. So for Alpha Omega, I have Alpha Map and Alpha RS support for online analysis, so you can get the data into the program while you are recording and do some analysis that's kind of more. For example, you can specify some analysis templates. You can do something like preset a number of analysis while you are recording, and kind of see the data as the experiment is going on. Actually, yeah, with Alpha RS, I'm not sure if Alpha Omega is pursuing this, because before they had I think COVID wave in February, I talked to George regularly, and then it kind of stopped. So I'm not sure what's going on. So what's the current status of Alpha RS? When are you releasing it?
The new version is going to release in end of this month. Here I have a question. Do we have all the online, all the functions the same as the offline? I mean
Yes, yes. So the online analysis is kind of limited. So it's mostly based on offline capabilities. And what happens online is that you specify how often you want to reset. So you specify first which channels you want to record and how often you reset the file. So basically, you record for 5 minutes and you run your analysis, and then every 5 minutes or how many minutes you specify, it resets again to no data, and then it kind of data accumulates again, and then you
Ah,
specify how often you want to analyze your data. For example, every 10 seconds. So every 10 seconds, you'll have an update of your analysis on your screen.
I got you. So the online
Mhm.
actually is based on the offline. So
Yes,
we
yes.
analyze on the existing data, not the real time data, right?
No, yes, no, it's based on real-time data, but
Mhm,
the way it works is based on the kind of software
mhm,
that was originally developed for offline. So
mhm,
so you have your online data, but
mhm,
you don't have your online data like something like scrolls.
mhm,
It just keeps more and more and more data points. And for
mhm,
example, you run, I don't know, spike triggered average or some kind of per event histogram or something for your receptive fields, and and every 10 seconds it will redraw the graph that will kind of show analysis results for the 10 seconds, 20 seconds, 30 seconds, etc. And then after 5 minutes, it will start again.
I see.
Mhm.
So it's kind of a delay, right? Like
Yes, yes,
no.
delayed. Yeah, delay, but you can go as often as 3 seconds, but it's not something that kind of recalculates all the time. So there is a separate thread in the
Mhm.
program that reads the data. So the data acquisition is not interfering with analysis, but it's a little delayed. Yes.
Okay, thank you.
Okay. So you can import not only data from your data acquisition system, you can read data from Excel, MATLAB, and text files, whatever, binary files. Now, lots of options are available for data import. NeuroExplorer supports more than 50 import of more than 50 file types. So you can also edit data. It's not only analyze. So you can, for example, digitally filter, continuous variables detect spikes, create new variables. There is a whole menu of operations on data variables. Visualization will go with what you can do with 1D viewer. Replay, it's like when you record from say a cell culture or from kind of a surface with the known position of electrodes, you can replay your data as a three-dimensional graph, like for replay neuronal activity. So what neurons are producing spikes, if you have any like waves of excitability or synchronous firing. It's a little kind of some feature of the program, but it's not that everybody's using it. So you can analyze different kinds of experiments. You can, for example, the left graph is for burst analysis that a lot of people who record from neuron culture use, and the right graph is for place cell analysis. So you have recordings plus coordinates of the animal, usually mouse. Graphics is publication quality. Uh, you can add a bit of graphics inside NeuroExplorer, and then you can export it to various graphics formats. We can talk about it, but mostly it's like bitmaps, meta files, and recently I've added um, another option for so-called SVG file, scalable vector graphics. You can analyze it in Adobe Illustrator. but every element then is editable. All the axes, all the labels, etc. You can also, if you need statistical tests like ANOVA, uh, our project is integrated, so you can have several scripts that you can execute inside our project. Yeah, then we'll use the save, restore, and reproduce analysis results. It's kind of a nice feature when you do something and you want to kind of remember your results and being able to restore this analysis later. And it includes the file, selection of channels, etc., etc. And finally, you can automate repetitive tasks using Python scripting. That's very, like, this is the specific script is one for one customer who told me that, oh, we are doing the same thing every time. I have to open a file, I have to rename like 6 channels, I have to add them for analysis in specific order, then I calculate spectrograms, add slide to PowerPoint, then I calculate power spectra. So he told me it's the same kind of set of steps, and I kind of spent an hour and wrote a little script for him, so he doesn't need to do those steps anymore. Okay, and then we have tutorials online. Some of them like go step by step, so you can point your customers to these tutorials, and they can kind of see how NeuroExplorer works in general. Okay, so this is all for the first part. For the second part, I would like to just open NeuroExplorer and show you how it works inside the program. Any questions?
I'm fine.
Thank you, Alex. Thank you,
Yes.
Alex. I have a question here.
Mhm.
So as you know, except for our neuroscience product, we also have some medical line products. So for the online analysis, so do we have some, experience in the past? I mean, some of your customer use the NeuroExplorer to do the, analysis online with NeuroOmega.
So what is the question?
So I mean, do we have some customer of of your product? I mean, to use your product together with NeuroOmega during the surgery. Do you have some experience before? For online, I mean, for online analysis.
Yeah, I'm not sure because my current support for Alpha Map, I don't know if it worked with your medical equipment. I'm not familiar, so it's a question to your software engineers in Israel. If it's the same protocol as Alpha Map, then probably yes, you can use it. But I know I worked with some kind of neurosurgeons in McGill University in Montreal, and but I think they used NeuroExplorer for offline analysis only. So I'm not sure if anybody used it online with the surgery.
Okay. I see. Yeah. Thank you.
You're welcome.
Yes. Yeah, Alex, actually, what Kai mentioned, the NeuroOmega is based on our older products. It's called SNR. It's the how say the format. It's format. It's the same. But I think there need some SDK to connect NeuroExplorer. I'm not sure how that we are now working on FRS and to make NeuroExplorer built-in, and that can do online. That is based on some SDK, or it's some other technology to make it.
Yes, my current Alpha Map support is kind of uses some protocol that your engineers sent me a long time ago. So with Alpha RS, it's much easier because it's just an SDK. So it's a library that I call and it gives me all the results. But in any case, if you need something like for a specific set of customers, I can always add like within some time frame, like month or two, I can add support for online analysis uh, for other Alpha Omega systems.
Okay, got you. Thank you.
Mhm. Okay, so if I put myself in the middle, is it blocking my NeuroExplorer screen?
Yeah.
Okay. So okay. Okay. I'll keep it in the corner. So is the program sharp? Can you see all the details and text and everything?
Yes, I can see all the details.
Yes, we can.
Okay, good. So I will start with so when you kind of work with your data, the standard first step is like depending, of course, on your experiment, etc. But you want to get rid of artifacts. So let's go with this step first. So we open a file, and then usually so first, yeah, this is another kind of good feature. You can show it to your customer, to your customers or potential customers. When you open data, for example, in MATLAB, uh, you have just names of the arrays and that's it. In your Explorer, you have immediate preview, so you can just open any file and you can see the preview of your continuous data, waveforms, and neurons. And each kind of panel is 1 second. So you have 1 second of data. This is the whole waveform, and this is 1 second of continuous data. So, and the next step you want to do usually is open 1D viewer, like this icon, or you can say view 1D data viewer window. And you can see something strange. So you have your neurons, you have your timestamps, and suddenly in like between 5 and 6 seconds, there are lots of spikes. And to zoom in, what you do is you keep pressing Control. That's what I'm doing, and scroll your mouse wheel, so you can kind of zoom in and zoom out on any place in your 1D viewer. So let's zoom in to this particular region, and you can see that it's kind of regular spikes. So of course it looks like it was stimulation. So it's just an artifact of stimulation. We can confirm it by adding, for example, continuous variables, and you can see the same thing. So it was stimulation, and if we now run analysis together with the stimulation period, we will get incorrect results. Our firing rate will be high, etc., etc. So how you can get rid of your stimulation, your artifacts in NeuroExplorer? So let's see if it's just one. Yeah, this is just one period. With the right click in this 1D viewer, there are lots of options. So I'm now pressing the right button on my mouse. First is doing nothing. Then you can add timestamps. You can add interval, and then let's use this one. On click and drag, select time interval, and delete all data in interval. So I do this. Now look, can you see the cursor? It has this X now. So I'm just saying, okay, I don't want this data. And of course, there's a warning that you cannot undo this. Boom. So now you have data, and now we're going back to the normal mouse mode. No artifact. We can see all the details, and the continuous channels look nice, and at least they look kind of without artifact. There is a gap, but the gaps actually in recording are supported by NeuroExplorer. So if you use any other or I don't know, like MATLAB based or EEG type analysis tool, they support only continuous recording. But here we can still like analyze channels with the gaps in the recording. So NeuroExplorer has lots of code to deal with the gaps and recording with some kind of episodes. So that's how you get rid of artifacts.
Hi,
Okay.
Alex. Sorry,
Yes.
one question. Is the 1D viewer available in your demo version?
Yes, but it shows only 10 seconds of
Okay.
the first 10 seconds of data.
Okay, thank you.
Okay, now let's.
Excuse me, Alex. Yeah.
Yes.
So, yeah, I have a question for the artifacts.
Mhm.
So sometimes maybe the customer prefer to filter out the artifacts, but not directly cut it off. So
Yeah,
yeah.
let's yeah. Yeah, I have an answer for you. The way to do this is there is another option. You can add interval. So create new interval variable, give it a name, noise or stimulation. Now I just drag from here to here. And now I have a new interval called stim. The next step, but we need to in NeuroExplorer, I don't know, probably you know already, you can analyze data, not only the whole kind of recorded data, but data from a set of time intervals, right? Just select data from these intervals and ignore the rest. To do this, we need to have set of intervals without this simulation, without the artifact. This is also done through 1D viewer. So you right click and say invert and select invert interval variable. Stim inverted, and we just say call it like no artifact with underscore. So you can see now we have this two intervals, no artifact, and we can now run analysis, for example, interspike interval histograms with data selection, all data. Let's see what we have. Yeah, so let's do log 10. So we see these intervals, and then we also, no, we need to actually have a large interval up to 20. So so this is no artifact. We don't need intervals. So this is probably, so this very long, no, let's say artifact. How often is it? It's about, so I think this particular peak is from the artifact, right? So we use all the data to analyze, and it's kind of basically all we see is just artifact data. So it's about 10 yeah, it was frequency every 10 milliseconds. So every 10 milliseconds we have the artifact, and this is the real data. So how to get rid of this one? We double click, go to data selection, and say interval filter, and we select interval filter no artifact. Oh, now everything's fine. So now we see real data, and data that was during simulation is not used for analysis. So that's how you deal with artifacts without destroying your data. Okay, is it?
Yeah, so if I'm understanding correct, so you mean we just ignore that noise single time period, and we just exclude them for calculation.
Yes.
But how about but sometimes, for example, some kind of noise is a long time. It's maybe affect the whole recording session. I mean, the time of the noise is pretty long. So, but we also want to trying to do the analysis. So maybe we need to filter it out. We need some kind of the noise template to to how to say to filter it out from the raw data and then continue the analysis.
Yes, yes. So if you have something like this, it's more like, for example, you have like, I don't know, 50 hertz or 60 hertz noise, and you want to subtract it from your continuous variables. This can be done by using operations on data variables. So there is a, if you go to edit, operations, one of the operations is linear combination. So if you have your noise, so for example, first you can subtract the reference channel. Suppose you have a reference channel that records mostly noise, then you can subtract it from your kind of real data channel. That's one option. Second option is if you have a template and you don't have a channel, it could be easily done in Python scripting. If it's So yeah, there are multiple options to deal with it. So for simple like reference channel subtraction, you can do it through the menu. If you need something kind of a little bit more sophisticated, it's very easy to do it with the Python scripting.
Okay, by the script. Okay, I see.
Okay.
Thank you.
Yeah, welcome. Okay, so now let's do, so I kind of started actually writing this presentation with actual spike train analysis, and I was thinking, but this is like a tutorial on how to analyze data, not how to use NeuroExplorer. But let's repeat this kind of. I have this series of steps. When you look at the data, at first you don't see what's going on and what features of the data you can reveal, and then we will use one analysis after another and kind of gradually reveal the features of the data. So I have this test file. It's mostly the test file that comes with a NeuroExplorer installer. We start with the 1D viewer. So we see, so we have the 6 neurons. Yeah, they kind of, sometimes they fire like many times a second. Sometimes there is a big gap. So first let's look at the visualizations. So you can visualize your neurons like this, or we can also add a continuous channel. Then we need to zoom in. It's not for the whole file, it's from another file. So this is just for drawing the data. See, for example, customers often need just to have a kind of representation of data for the publication. And I had a request actually from China, specify color for continuous variable. So you can specify a different color, let's say blue, if you want to have several colors. Signal, no signal, we don't need signal. We do second channel. So this is one way. And then when you want to export graphics to some other application, for example, Illustrator or some other plot package, you go to graphics, export, and then we have these several options: clipboard, meta file, enhanced, PNG, TIFF, scalable vector graphics. and finally send to PowerPoint. So you can, I don't know if you know about this feature, but I'll just show you how it works. You specify PowerPoint file, you specify the title, and press OK, and it opens PowerPoint. And you have your kind of graphics inside the PowerPoint as a slide. So you can keep kind of generating different graphs and sending them to PowerPoint, and then you have your kind of story of your analysis. This another analysis that's mostly used for drawing is rasters. So we can do something like this. So press rasters. The only parameter is start and x minimum and x maximum. You can also specify y-axis, and here you can like remove some of the channels. You can also specify single column, so they go one on top of another, and this will be your picture. But there's no way to specify the color here, but you can go to graphics, export, and if you use metafile or SVG, you can then change the color, because each element will be editable. So okay, so now we went through this okay, so we just went through the way of how I represent data and show my raw data in a paper. The next type of analysis, usually people ask a question: what if, so do I have neurons firing at the same rate? Obviously, for neuron 04A is firing faster than the others, and the color here is actually shown on this kind of color ramp. So the red one means that it's faster, so I cannot draw it within the 1 pixel. So it goes from display pixels, change the color of the pixel if there are many spikes within the same pixel. Okay, so let's look at the just firing rates. If it's similar, or we see that it has some gaps, but just look at the histogram. So basically each of the, so it says bin 10 seconds. So for each 10 seconds we calculate number of spikes within this bin. Yeah, it's kind of going up and down. What actually people, so we don't see any pattern here. What several people use, I mean, especially from the pharmaceutical companies, they may have like initial period when they have a cell culture with just, some kind of baseline, and then they apply a drug, and then they and then they look at the changes in the firing structure and frequency after the drug. If it goes faster, if it will be with more bursty, etc. So here we can just let's first make a huge bin, like let's say a bin of 500 seconds, and go to 2000. Yeah, so we see that some neurons really change firing rates. So from and we can also change the spikes per second, so we can see firing rates actually. So yeah, so the neurons actually did change firing rates over the long periods of time. So for this pharmaceutical experiments, the problem is that sometimes you cannot specify kind of exact bins. Like we have this huge bin of 500, but what if our pre-drug period was from 0 to 900, and then drug period was like from 1000 to 1700? To do this, you use firing rates analysis. So we go from 0 to first period will be to 900, and then this second period will be like from 1100 to 2000. So this is how you specify kind of intervals that cannot be expressed in terms of bins. So we have period 1 and period 2. So if we apply the drug, for example, in period 2, so we can see that neuron 06D increased firing rate almost by a factor of 2. So that's another analysis, simple analysis to look at your kind of changes in frequency. So that's a trivial thing. Next level of analysis. Let's look at the structure of this firing rate, of the firing patterns of neurons. So the typical, you probably know, I don't know, tell me if it's kind of too simple and I'm kind of talking too much about things that you already know. But usually, if you look at any kind of spike train analysis tutorial, the next step is to analyze interspike intervals. And to do this, you use interspike interval histogram. We already saw in our artifact demo. Yeah, that's too much. Usually I go from 0 to 0.5. Okay, so this is typical for kind of for neurons. So we have like a lot of spikes with very small interspike interval, and then it kind of exponentially decays. Interesting. And the first neuron is kind of, yeah, looks totally random, but in 6D and 7A we see these little peaks. What they represent? They represent the fact that sometimes we have spikes that kind of separated by about like 0.8, 80 milliseconds. So we have spikes. So what this interspike interval histogram shows? It shows a probability. We can change the value to probability. Probability of a spike in the same neuron based on the assumption that there is a spike at time 0. So what is the probability of the next spike will be at like 80 milliseconds later, the previous spike. So that's this peak. So we have some kind of regular firing within this neuron, but we don't know the details yet. So let's look at another way of looking at very similar properties. It's called autocorrelograms. Do you know, do you need explanation what it is?
Yes, Alex.
Okay. So when we had this interspike interval histogram, it was a probability of the first spike. So autocorrelogram shows probability of any spike based on the assumption that we have a spike at time 0. So it means that we have spike at time 0, and very probable that will be another spike within a small period of time. Then the probability goes kind of down, and then it goes up again. But this time it's a huge peak. So compared to we can look at if we look only at spikes kind of after 0, so we can compare it to interspike interval histogram. So this is autocorrelograms, and if we go back to the histograms, we say 0.2 bin seconds. Okay, you see it's a very small peak, but if we go to autocorrelograms, by the way, I just used this undo redo buttons on the toolbar, so we can go to the previous result. So this is our last result, this is the previous one. So now we see the probability of any spike. So it could be the first spike, the third spike. So what a correlogram is like you probably, I need to send you a link to the explanation But the idea is that you have a spike train, and then you look kind of from the top and align your eye with the spike, with one of the spikes, and then you look left and right, and you have these little bins. And if you see, like, if your bin is 1 millisecond, you have a spike in 8 milliseconds after, then bin number 8 gets a bump, then you go to another spike, then you look at all the spikes around it, etc., etc. So that's what we did here, and we see that there are lots of spikes that happen. Like we look at the spike here, and then spike. There are lots of spikes that are about 80 milliseconds after this spike, and then also before this one. So why is such a difference between? So why there is a difference between no this one and uh, this and interspike interval histograms? Because probably, so with the histogram, so we have exact spikes, like spike and then 80 milliseconds, another spike, another 80, another 80. But what happens, what we see here is that we have a spike, and then maybe spike maybe at 80, maybe there is a spike that kind of very close to this one, and then at 80, etc., etc. So so that's how we kind of understand that it's not, so that the peak that we see in interspike interval histograms, that's why it's so small, because it's not often that we see the exact, so there is nothing between this spike and the spike that comes 80 milliseconds after. So it's empty period. Usually there is something else. We can also kind of confirm this by using Poincaré maps. What's this one is showing? Let me just show you the graphs. This one is showing, so now we want to look at the relationship between this spike and the next one. So if we plot, I don't know if I'll just make this a little bigger. If we plot this interspike interval on x-axis and the next one on y, so what we see with 4a, it's random. So we have interval here, and the next one could be anywhere. When we look at 6D or even 7A, if we have an interspike interval around 80, the next one could be actually just 1 millisecond, could be 10, so lots of other values. And then there is this blob, shows that the next spike is actually also around 80 milliseconds. So this particular graph is called Poincaré plot. So previous versus next interval, and it shows that some neurons have no relationship between this and next, and some neurons have relationship in the way that we have lots of kind of smaller interspike intervals, and then a lot of intervals that are the same kind of the same value, around 80 milliseconds. So that's another analysis. So what we're still working on, how to represent the structure of a single spike train. The next analysis that people often use is burst analysis, but we will not use it for this file. We can look at the burst file, and if we zoom out, see what we have here. Yeah, you can see that the neurons kind of, they have this period of inactivity, and then what is called burst. So we have a small interval that starts kind of this period of activity, and then several spikes that go kind of one after another in very short burst. That's why it's called burst interval. So we have analysis that will identify start and end of this burst. So should I maybe I wouldn't do this because it's already like 7:53. So but I don't know, do you have any customers in pharmaceutical? Companies?
No company, but
No, okay. Because or pharmaceutical or people who record from cell culture. Because with cell cultures, you have this bursts all the time. So the neurons kind of grow and make connections, and then they start kind of firing together. And one fires, it kind of excites other neurons, and that's why it kind of the whole network fires at the same time. Okay, so now let's. So we saw this autocorrelograms. So interesting results. So we have this huge peak, but uh, this is this autocorrelogram is calculated over 2000 seconds. What if we calculated on a different on for some kind of for smaller subset of data? So let's do so in NeuroExplorer you have this data selection, and you can say, okay, instead of all the data, I want to use from 0 to say 500. Boom, nothing. We don't see peaks. What if we do from analysis from say 1000 to 1500? Oops, huge, huge peaks. It means that we have lots of spikes at regular intervals. So what we just discovered is that sometimes when we kind of do the analysis on over all the experiment, we don't see the details in terms of the sort of inside experience. So this is behavioral experiment. It's not there's no stimulation, just freely moving red. So in some kind of periods of activity, actually, were represented by some kind of changes in the firing pattern. So how do we look at these changes? We go to we want to look at this histogram, kind of make it vertical, and instead of peaks, just use the color, and then use the sliding window to calculate the same thing over time during experiment. Okay, it's called autocorrelogram versus time. Okay, so what we see, so before we had just one, so if you summarize in this direction, now we have time from 0 to 2000, and we can see that it's almost for a long time. So each vertical line is autocorrelogram for a short window. For for a long time there's nothing there, and then suddenly we have a period around like 1200 seconds where there is a lot of activity that's kind of goes in regular intervals. We can visualize the same on spike by spike basis using per-event rasters. So now we do this, and it's another analysis. So per-event raster is kind of shows you. So we take a reference of one of the neurons. So guys, tell me if it's something that completely out of the main idea is that there are this 40 analysis types, and you start looking at your data. First you see, okay, I have this time ticks. Then you say, okay, maybe the frequency changes. Yes, there are regular intervals every 80 milliseconds. Yes, then these intervals are not uh, represented in all the recording. They were kind of in some kind of short time periods actually. That's what we see here. So these are the periods of overall activity. Then the next step is then we look. So when we kind of go back to the spike trains, we can ask a question. do we have any dependency? So are those spike trains independent, just random? Yeah, they look random. They have kind of typical neuronal distribution, a lot of short intervals, smaller number of large intervals. But the question is, do you have any relationship? Like if the new one of these neuron fires, like 6D, what is the probability of another neuron firing within some kind of short time period? So that's this is where we go to peri-event histograms and cross correlograms. So that's actually what let's see what's the time data selection. I'll just use all. So we can see that actually when the neuron 6 fires, neuron 5B also fires with a very high probability. So you're kind of in neuroscience, you can think about what's the functional kind of consequence of this. Is this do this usually, because usually record kind of two neurons close together? Is it like one neuron has like its kind of axon goes to the dendrite of another neuron, when it fires it excites, another neuron fires, or this is so-called common input, and these neurons they fire as a group together. So, but there's no kind of causal relationship between one neuron firing and another one also fires because of the first one.
Excuse me.
So we can also look at this at this particular kind of trying
Excuse
to
me,
answer the
Alex.
question. Uh-huh.
Alex, sorry. Can I ask you a question?
Yeah, sure.
Yes, here I look at this picture. Actually, I think that time negative, there's low actual data. But here you can draw a picture like minus 0.2. How this works?
Yeah, so basically what we see here, this is called so-called cross-correlogram. What we so this cross-correlogram shows that if we have a spike in one neuron, was there a spike before this spike in another neuron? What's the probability? So that's why we have negative time.
Oh,
Because, for example, what if neuron 5B fired always before 6D? Then we need to kind of, if we look at this 6D and then your 5B, okay, so it was every time we see a spike in 6D, there was a spike in 5B that was before this spike. That's why we have this negative and positive.
okay.
So it's like you can if you know the cross correlogram, not cross correlogram, cross correlation analysis of analog signals. So basically, when you have one signal and another signal, and if kind of it's when the one of the like electrodes goes voltage goes higher, and then on another one it goes higher before that, then you'll have kind of similar. It's called correlation graph.
Get
But here we just look at the spike of one of the neurons, in this case 6D, and see what's going on before and after. Kind of align all the other spike trains around the spikes of this neuron.
Okay, thank you.
Okay, so maybe so peri-event rasters actually shows the same thing, but all this alignment, but kind of over time. So this is the sum, and this is what happens from the first spike in 6D to the last one. But since it's kind of not maybe kind of too technical, let's see what we can do next. We can do something like, if you want me to keep going over analysis, another kind of standard analysis is coherence. When you look at so if you have deep, spike trains that kind of are correlated, you want to look at what frequency they're correlated. It's called coherence. So we go to regularity, coherence analysis, and the coherence analysis shows kind of dependency of signals based on the frequency. So you decompose each signal into sine and cosine, and then of different frequencies, and then you look at correlations of all this of coefficients of this sines and cosines at different frequencies, and we see kind of confirmation that at about 11 hertz we have a much higher correlation between neurons than at any other frequency. This is called coherence analysis. Okay, so it's already we have like 25 minutes left. We can go through some other kind of features of the programs, like what menus you use, how you do this, how you do that, instead of just going through analysis. That's why when you ask me about write up on what kind of features will be useful for your customers, you have to explain each analysis. For you to, so maybe, I don't know, for you to explain it to the customer. So if they're interested in, for example, structure of their spike trains, or they want to find one of the difficult tasks. For example, I have special analysis for this was when people record from neurons, but also from kind of local field potential, and they want to find if with a specific kind of conditions, you see like theta rhythms, some kind of oscillations on the surface of the brain, or in some kind of area that's not one neuron but just a large group of neurons, and then they want to see if some separate neurons are firing in phase. So if we have like a group of neurons doing oscillations, how about individual neurons? Do they fire within phase or different phases? So that's another kind of complicated question that you can answer with one of the analysis in NeuroExplorer. Let me show you then just convenience features. So one of the ways of going through your analysis and then recording what you just did, and recording all your results, there is the save results menu. For example, let's first work with graphics. How can we fill the kind of the area under the graph? We say edit graphics, graph properties, and say fill the color under the graph. So that's how we make this type of graph instead of just one line. Second, if we want to save this result and restore it later, we select the save results menu, and the first one is quick save results. So nothing happened, but it actually goes to a kind of results folder in your user documents. So if we go to again to save results, and the last item in this submenu is folder summary. So this is what I prepared for this actual presentation. So every time we just press this one, coherence analysis. We have other analysis that I saved today. Detect spikes, perievent raster, perievent histograms, so you can detect spikes in NeuroExplorer. For example, if we want to reproduce so these are just saved results. If we double click on one of them, for example this one, perievent rasters for continuous, it shows the actual graphics, and then we have numerical results, we have parameters. But what if we want to go back? So to go back to the same analysis, it's kind of difficult without saving using this menu or there is another menu called template, because what you need to do to reproduce your result, you need to open the same file, you need to select the same channel, and you need to specify like about 100, if you include all the labels and everything, parameters in your analysis. So and it's kind of, you have to, and these numbers change, and you have to write them down or save somewhere. But here it's much easier. So if we want to save results, and this is a saved result, and we right click, we can just click on Restore Analysis in NeuroExplorer. So what happens when you select this menu command? NeuroExplorer will open the data file. It will select the variables that we used in analysis. It will specify parameters of the analysis and run the analysis again. So it kind of live. So this looks the same, but actually it's a live analysis that you can kind of change parameters now. You can do smaller, wider window, etc., etc. Also, just the basics of each analysis. If we calculate, for example, the same coherence analysis, so not only we have graphical results, we have numerical results. If you go to View, Numerical Results window, so we have for each frequency value, we have the value of the coherence. So these are all the kind of results, and it shows with the color where the high values are. And with numerical results, we have two tabs, results and summary. So with summary, we have something like minimum, maximum, etc., mean frequency, etc., confidence level for this analysis. So that's the kind of the basics of each analysis is will have this feature. So you have the graphs, and then if you want to look at the numbers, you go to View, Numerical Results window, and there is a button on the toolbar. And from here, if you want to like plot your values in Excel, you can click on results, numerical results, like send numerical results to Excel. So it will ask you a bunch of questions. Press OK, opens Excel. Now all your values are in Excel, so now you can just draw a picture, graph inside Excel if you want. The same goes for MATLAB. You can, for example, export in MATLAB menu. You can send selected variables. You can send numerical results. So let's do the analysis again. And with MATLAB, it says say numerical results to MATLAB. Opens MATLAB and then sends the vectors of results to MATLAB. So which one is here? It's done. It should be visible now. Okay. Command window, current folder. Yeah, these are the results. So this is, we have this next matrix with all the numerical results. Okay. And finally, scripting to, you can a little bit, you can automate some of the things that you do by recording macro, or you can use like new script or open script, like for example, what did I do? So for Eli, so this is the script that renames the channels, then selects the channels, and then applies the template. That's how you run analysis, and then you send graphics to PowerPoint, and then you run another analysis, then you open the 1D viewer, and then create another file in another slide in PowerPoint. So this is all can be done in scripting, and scripting has a kind of full full set of functions, and you can view them here in the sort of online, not online, it's like a internal help file, and for each function you have a simple code that you can use to kind of learn how to use this function. Okay, so I don't know if what's kind of jumping back and forth, but maybe it's time for questions. We have 15 minutes left.
Yeah, thank you, Alex. So I have a question. So some of our medical customer they ask how to use the NeuroExplorer to do the power spectral density analysis. Because for example, some of the disease, some of the symptoms of PD, the oscillation is related to the symptoms. So yeah, so the researchers are interested in the oscillation, some kind of the beta band or theta band, and yeah. So can you give a
Yeah, sure.
brief?
Yes, I can show you. I have something in like saved results. So first we can do. So this is a spectrogram. Like this is kind of artificial signal that I generated, and the spectrogram shows you a spectra for a sliding window. So it shows that there is like 8 hertz oscillation. So for example, it could be theta or a little higher frequency range. So to do this, so let's just restore analysis. So we have this data file. So let's just close everything. Go back. Actually, there is one nice feature is you can always restore the last analysis after you close everything. So it loads the data file and runs the last analysis with the results. So for this particular signal, we can go to analysis of continuous data, and we have just power spectra for continuous. Power spectra is kind of very sophisticated analysis. You can do multiple tapers if you know what it is. Multiple tapers is usually when you don't have kind of a clear presence of specific frequency, and you want to apply different kind of different windows on the same signal, and then calculate the power spectra. So we just use single taper for now. So, and this is all the frequency you have for the signal. Usually you, so I mean, if we're interested in low frequencies, all you do is just say, okay, I want to see frequency only from 0 to say 100 instead of 500. So now you can see this peak. So this peak is due to this, signal, due to this kind of 2 periods of slow frequency activities. So this is a per events power spectra. Then we have these spectrograms that I showed you before. So the spectrogram shows you not again like we did with the neurons. It shows you not the overall kind of average spectra, but it kind of uses a sliding window that goes from start to end, and then for each of these windows it calculates a spectrum, then we can see that this kind of artificial signal has these two periods of kind of high activity around 8 hertz. Then we have per-event spectrograms. This is another analysis that's used for example, usually for stimulation. So, for example, you have a stimulation and your continuous signal has a little bit of oscillation after each stimulus. But if you just analyze each after stimulus period, you don't see much. I mean, it's very kind of subtle. But what if kind of still repetitive, and what you can do here is that you can calculate spectrum of the signal after first stimulus, then spectrum of the second stimulus, the next, and then average them. And then after you average like over 100 stimuli, you have kind of visible presence of specific frequency, for example, theta rhythm. So there is single trial. We have, so there are like probably about 10 analyses related to oscillations, Hilbert transform, find oscillations, not 10, maybe like 6. So find oscillation is this complicated analysis where it filters the signal first, then looks at the frequency bands, and then if one band is higher than the other, it declares this to be a kind of, we can do this for this signal. So let's go back to saved results, and I have it. Find oscillations, pyramid rasters, find oscillations. So what this particular analysis is done is that it calculates this kind of power of specific band, like for this time is a theta signal, theta band, and then it creates a number of variables. So if we go to the first window, it actually created signal theta 0 phase. That's the start of each of the wave of this theta phase. So let's go here and add those variables. So let's do signal theta epochs. So it identified that we have 2 epochs of oscillations. Then we go single theta filtered. Then it filtered the signals, and it shows you the kind of nice clean signal during these periods. And then it also shows you the start of each oscillation. So you can now relate these specific timestamps to your neurons and see if they fire within a specific kind of phase of the oscillation. Sorry for the long, but yeah, so basically if your customers are interested in this type of analysis, lots of analysis can be done in NeuroExplorer. And the last one is band energy versus time. So if they want to look at only at like theta band versus time, they can plot like how much energy was in theta band during the experiment. Okay, so next question.
Alex, sorry, David, please.
No, I just curious because there's a features detect spikes, and what is the differences between detect spike and our function like spike sorting? Is it just reflecting the frequency of the spikes?
No, this is just some customers, when they record with a very simple equipment like with MATLAB or Texas Instruments, they just record continuous signals, and they didn't care about the spike sorting. They wanted basically all the spikes from the signal. So I added this detect spikes analysis to just detect spikes, just looking at the threshold crossing. That's all. But currently there is no spike sorting in NeuroExplorer.
I see.
So it's for your customers, they probably will never use it if they have your own spike detector that already kind of supersedes this one.
Got you. Thank you.
Yeah,
Yes.
Alex, I would like ask some general questions regarding NeuroExplorer. So now, how many functions do we have in the analysis?
I think it's about 40.
40, right? So
Yeah, 40.
okay. So in the
Because
help of the please, yeah.
Gunya, go ahead.
Yeah, I mean, there is a help function in the software. Can we find all the analysis, how to say, the description for each functions? And
Yes.
yeah, so
Yeah, you can
what?
also do this in with online help, like documentation. But it's so with how to guides, you have first, so you have with the tutorials, you have a few analysis kind of described step by step. How to guides is mostly like importing data, dealing with license scares,
Yes.
and but the main information is in reference. So you
Okay.
go to analysis reference, then you have analysis types, and
Okay.
like interspike interval histograms. It
Okay.
explains each, so general definition what it is, and then each
Okay.
parameter, and then how, and then what values are shown in the summary and the algorithm. So you have this for each analysis.
Okay. Okay, that's great. This is only for online, or all the customer in also built in the NeuroExplorer software.
Yes, yes, yes. All this kind of, I have three types of documentation: online, PDF file, and internal in the program. They all are generated from the same source.
Okay,
So,
thank you.
like if you go to help topics, this is the same thing. Like now we have
I see.
reference and
Okay.
analysis.